So what they start introducing you to is just going back to the basics and looking at problems and trying to figure out what you need to do in order to solve them. And so they've given us 3 examples here that look very, very similar, but when it comes to integration, it makes a huge difference as to what you can do with them. The first one is 4 over x squared plus 9. Then we have 4x over x squared plus 9, and then we have 4x squared over x squared plus 9. And it seems like it wouldn't be that big of a deal, but it makes a huge difference. For the first one, we look at it and we can't use substitution. Why not? What my u would probably be x squared plus 9. What would my du be? Du would be 2x. What's the problem here? There's no x, right? If we look at b, we could potentially use substitution there, right? Because all I have to do is multiply by 2. And then if we look at c, we definitely could not use substitution there because we need an x squared and we would get a 2x, right? So your first thought would probably go to substitution because that's the easiest one. So the middle one's probably going to be the easiest one here for us to deal with. The other thing you're going to look at is, well then, we have done integration in the past with a square and a square. 9 is a perfect square. So if you flip really quickly to page 484, they have kindly listed every integration that we have done for the whole year. And so if you scan down that list, you should see one with a squared and a squared. And so our a then would be actually 9 because the a is the constant. And the b would be the x, right? Or the u rather would be the x. So if I were to rewrite this, I have x, right, to the second power. That's my u. And I have 3 to the second power. That's my a. The 4 is just a constant, so I can pull the 4 out in front and do the integration then of my dx over, and I can rewrite it just so it looks exactly the same, 3 squared plus x squared. And then my antiderivative here, I have to put the 4 in front, so I have the 4 there. It's going to be, what is my antiderivative of something that looks like this? 1 over what? Which is 3 for us. And then arctangent, right, of u, which is x, over a, which is 3, plus c. Now, you can, when you simplify this, and hopefully they did that, you're going to go ahead and multiply that 4 to the 1/3. So it ends up looking like this. 4/3 arctangent of x over 3 plus c. And so that's one type of integration that we've done. So if I look at the middle one, I can use substitution, but what do I need to do to make it perfect? So if my u then is x squared plus 9, my du is going to be 2x dx. What do I need? 4. So I need to do what? Multiply by 2. And so for this one, I have 2, and then I have 1 over u du. Correct? What is my antiderivative for 1 over u? Natural log, right? So I would say 2 times the natural log of u plus c. And then what's my last step here? Yeah, I need to take this guy and plug it back in. So I have 2 natural log of x squared plus 9 plus c. All right? 2 natural log of x squared plus 9 plus c. And you can put parentheses or absolute value there. You really don't have to have absolute value. Why not? Why don't I need absolute value around x squared plus 9? It will never be negative, right? Never be negative. If it was minus 9, that would be a different story, but a square plus a number will never be negative. All right, and then the last one. So this last one is a little bit, I feel like this is the one we think of the least. All right, and I feel like every time I give it on a test, y'all overthink it. But the method here is when you have the same degree on top and bottom, or a higher degree on top than bottom, what do? And so I think this is a method that no one ever thinks about, but you actually need to do long division. So we're going to say x squared plus 9 into the 4x. Well, x squared goes into 4x 4 times, and you get 4x squared plus 36, right? And then you, of course, add the opposite there, so you make those subtraction. 4x minus 4x squared, that cancels out, and then we have that negative 36, which just becomes our numerator, negative 36 over x squared plus 9. And so now we need to do that integration. And so if I do that integration, then I have just a 4 minus 36 over x squared plus 9 dx. And remember, I can do those individually, right? And so if I do those individually, what's the antiderivative of just a constant? To multiply by x, right? And this guy should look familiar. We just did that integration, didn't we? Like, I mean, that's literally the same integration we just did. It's just multiplied by 36, right? So it ends up being minus 36 times my a is 3, right? My u is x, so 1/3 arctangent of x over 3 plus c. And then we can just multiply that over. We get 4x minus 36 times 1/3 is 12. Arctangent of x over 3 plus c. And while when we started out, they all looked very similar, you can see from the answers that we got that you get completely different answers here than what we started out with. That one variable made a huge difference in the method that you used and the answer that you got when you took your antiderivative. So your u here would be the denominator. So u would be x squared plus 2x minus 4. Du would be 2x plus 2 dx. We just want x plus 1. So if you pull a 2 out, you would get 1/2. Du equals x plus 1 dx, which is what we want. And so when you plug that in, you have that 1/2. And you have 1 over the square root of u, du. Well, you can rewrite that guy, 1/2 u to the negative 1/2, right? Du. And then your antiderivative is to add 1 and divide by the new. So the new exponent is just going to be positive 1/2. And then dividing by 1/2 is multiplying by 2. And so you just cancel these, replace your u with what your u was. That's x squared plus 2x minus 4 to the 1/2 or square root plus c. So for this guy, we would use long division. So we would say 2x divided by x minus 4. So x goes into 2x twice. We get 2x minus 8. We are subtracting here, so it's adding the opposite. Those cancel, and you're left with just a remainder of 8. So we have 8 over x minus 4. All right, and then we take that integration here. So we do the integration of 2 plus 8 over x minus 4 dx. For the 2, we just have 2x. This is going to be 8 times the natural log of that guy. 8 natural log of x minus 4, and then plus c. Let's look at this guy. We have a 4 minus x squared, which is indicative of what? 2 squared minus x squared. That's indicative of an arc, right? One of the arcs, right? Specifically, it's going to be sine. Secant has the function on the outside too. But my problem is they have an x plus 3 in the numerator. which causes an issue all the way around if I'm trying to use my arc sine. Arc sine really just needs a number up there. So when I have a numerator that is a binomial or trinomial or anything that has plus or minus in between my terms, I can separate my numerator. So like 1/3 plus 1/3 is 1 plus 1 over 3, right? And that's what this is. This is two things over a denominator. So it's one of them over the denominator plus the other one over the denominator. That's how you split up fractions if you want to, or if you need to. And so I can rewrite this guy as x over the square root of 4 minus x squared and 3 over the square root of 4 minus x squared. And then I can actually use two different methods for those. I can use one method for the one that has the x on top, and I can use another method for the one that has the constant on top, all right? For the one that has the variable, I can just use u substitution. So if I look at this first one, my u would be 4 minus x squared. My du would be negative 2x dx, right? I don't want a negative 2. I want just a 1. So if I multiply both sides by negative 1/2, then I will get my x dx, which is what I'm looking for. And so I have, for this first one, negative 1/2, 0 to 1, of just u to the negative 1/2, right? Make sense? For this second one, I'm going to use an arc, right? Specifically, if you look at your list, you have a number squared minus a function squared. That is arc sine, right? And it's just going to be the arc sine of the function over the number. And so my function here is x. My number here is 2. 2 squared, x squared. And so I have this 3, which is just a constant. And my arc. That's how I'm going to take that antiderivative here. So I have the 3. And then I just have my dx over my 2, which is squared, and my u, which is x squared. And now I can take my antiderivatives. Antiderivative of this guy, I add 1, right? Negative 1/2 plus 1 is positive 1/2, so u to the 1/2. And then I divide by that 1/2, which is multiplying by 2. Right, so I just get negative 1. My u was 4 minus x squared. For this one, I'm going to say 3 times my arc sine of my u, which is x, over my number, which is 2. And I am doing that from 0 to 1. And then you can just plug it in, right? Plug in a 1, you get negative square root of 3 plus 3 arc sine of 1/2. What is the arc sine of 1/2? What degree, or I guess they do it in radians, gives you a sine of 1/2? It's a 30-degree angle, so it's pi over what? Pi over 6. Yeah, so 3 times pi over 6, right? That would be what happens when I plug in a 1. And then what happens when I plug in a 0? Well, 4 minus 0 is 4. The square root of 4 is 2. Negative 1 times 2 is negative 2. Plus arc sine of 0. What gives you a sine of 0? 0. So we have 0 times 3, which is 0. And when you plug all of that in, you're going to get approximately 1.839. So if you split this guy up, or use long division, whatever you do, it's the same concept. You have x over x minus 2 over x dx. X over x obviously simplifies to 1. So I have the antiderivative of 1, which is just 1x, minus the antiderivative of 2 over x is going to be 2 natural log of x. And I'm doing that from 1 to 2. And so if I plug in a 2, I get 2 minus 2 natural log of 2. And then I get minus 1 minus 2 natural log of 1. Natural log of 1 is 0. Not any log of 1 is 0. So I end up with just a 0 there. So I have 2 minus 1, which is 1, minus 2 natural log of 2. And when you put that into a calculator, you get a negative. Yes, negative, what did I say, 0.386? So, all right, let's look at this one. Evaluate, and they give us x squared over 16 minus x to the 6th. So when you see anything to an even power, it can be something squared, period, right? So just divided by 2, right? So I can rewrite this to make it look like something that should be very familiar. So 4 squared minus x cubed squared. What is that? That's a number squared minus a function squared. Arc sine, it's arc sine, right? Tan is your plus without a root. So my u here, so I can use my arc sine and use substitution, right? And so I could say that u equals x cubed. Du then is going to be 2x squared dx. I don't want 2x squared dx. What do I want? I just want x squared, so I'm going to say 1/2 du equals x squared dx, which is exactly what I need. So I end up with 1/2 dx over the square root of 4 squared minus u squared. 2. It's not 2. It's 3, which makes that 3, which makes that 3. There we go. And so now I have a perfect arc sine, right? My arc sine is what, 1/3 is going to go there. And then I have arc sine of my function. What is my function? Here is just the u, right? Over the a, which is 4, plus c. And then I do want to go back and replace my u with what it was. So 1/3 arc sine x cubed over 4 plus c. That this first one that we look at here, what you'll find is they're not giving you ones like, okay, you're going to see this exact one, you do it the same way every single time. Like, that's not what we're doing here. Now we're starting to throw things at you from all directions, right? And you look at this guy and you're like, I can't do anything with him. What do you want me to do? And I will say this one's not intuitive. The next one is. The next one's very logical. The next two are to me. This one is something that I relate it to almost like when we were doing trig proofs.
and you had to multiply the top and the bottom by the conjugate so that you got a sine squared plus a cosine squared, right? You remember that? So if you had like sine minus cosine and you're like, well, but it's not exactly what I need. And so you could multiply by the conjugate and you could get one that looked like one of your trig identities potentially, okay? And so that's what they do here. So in this one, you're like, well, I have a 1 and I have a 1 plus e to the x. If I do a natural log here, I have a problem because the derivative of 1 plus e to the x is e to the x. So I really need an e to the x on the top. And so that's what they do. They literally add and subtract an e to the x on top. And so we have 1 and we add e to the x and we subtract e to the x. I have not changed that 1, right? 1 plus 2 minus 2 is still 1, right? And then they have it over 1 plus e to the x. How does this help? Well, this helps because I can now split it up. And so they call it the disguised form of the log rule because you can force it to be a log by doing this. So now I can split this up and I can say, well, I can do 1 plus e to the x over the denominator. And I can subtract e to the x over the denominator. Again, I haven't changed it. I have now just split it up. But all of a sudden, I have something I can do. 1 plus e to the x over 1 plus e to the x is just 1, right? And this guy is now a perfect log. My denominator is 1 plus e to the x. My derivative of 1 plus e to the x is e to the x. So I have a perfect log antiderivative here. Does that make sense? So my bottom, my top is my perfect derivative of that. So I can actually just do a natural log here. It's going to be 1 over u. All right, and so my antiderivative here then, antiderivative of 1, well, that's just x. Antiderivative of anything in the denominator to the first power is the natural log of that guy. And we said my u was 1 plus e to the x. And then, of course, my plus c. And that's a minus. Sorry, I wrote it wrong. And so it doesn't look like a log one when you first do it. But when you manipulate it, you can force it to be 1. So this is a disguised form of the power rule, and I don't think it's actually as disguised as it seems to be for me. So in this case, you really want to think about what's my most difficult function here. My most difficult function here is, of course, the natural log of sine. And so I can actually just use straight u substitution here. U is the natural log of sine. Du then would be my derivative of sine, cosine, right, over sine. That's the du of a natural log, dx. Well, I just so happen to have that guy right there, right? So I really have a perfect u substitution, a really easy antiderivative. Antiderivative of u, well, that's just u squared over 2, right? Or 1/2 u squared. And then if I substitute my u back in, 1/2 natural log of sine of x, and this guy is squared. That's way more intuitive to me than the other one. You naturally see that one a little bit easier. When you have the natural log of a function, so natural log of some function, the derivative of that is the function's derivative over the function itself. No, not don't do the derivative. So the function is sine x, so the derivative of sine is cosine over sine, which is cotangent. Trigonometric identities. If you didn't use them enough last year. They are in the back of your book. Well, they should be. They're in the back of my book. So if you flip all the way to the back cover, honestly, the ones that you'll see, you probably remember, which is the Pythagorean identities, which is what's used here. But to the back of your book, the hardcover has all of your trig identities pretty much. You have your reciprocal, which hopefully you know like the back of your hand, your tangent, cotangent, which we just used. Pythagorean identities, the ones you're not as familiar with, but we did do our cofunction identities reduction, we did sum and difference, and we did double angle. We didn't really use power reducing as much, or sum to product. But the ones Pythagorean identities, hopefully you can't forget them. But, just in case. They're there. So when you look at this particular guy's tangent squared, even if we changed it to sine squared over cosine squared, it's not going to help us. Because even if my u is cosine squared, my du would be 2, times sine. It just still wouldn't work. We still wouldn't have a sine squared in there, right? And so when we look at something like tangent, it's easier to rewrite it. First of all, we have a 2x, which is kind of a pain. So rewrite it out of the 2x. If this was my u, my du would have to be by 1/2 because we have to get it out. So they first rewrote it like this just to get the 2x out of there. But then we still have another issue. It's that we don't have an antiderivative for tangent squared. Like not even in our natural log ones do we have an antiderivative for tangent squared. And so that's where you want to possibly rewrite it to one that we have a perfect derivative for. And so if you'll remember, tangent squared plus 1 equals secant squared. So I can rewrite tangent squared x minus 1. And so I actually want to replace, I'm not doing u substitution here, I'm literally just doing substitution by trigonometric properties here. So it's not like u substitution where you do the derivative. I'm literally just substituting, like if I had sine squared plus cosine squared, I would definitely change that to 1 and take the antiderivative of that, So all I'm doing is replacing it. I'm not doing like a u substitution. So I'm just going to write, instead of tangent squared of u, I'm going to say secant squared of u minus 1. And I do have a perfect antiderivative for secant squared. What is the antiderivative of secant squared? So this guy is just tangent. So tangent of u. And then minus, what's the antiderivative of 1? It's just 1x. And I do need to replace this u, right? At the very beginning, remember u was 2x. That's why I have that 1/2 in front of it. You could have left the 2x the whole time as long as you know that it's a 1/2 when you do it. But so I end up with 1/2 tangent of 2x minus x. And of course, plus c. Always add your plus c when it is indefinite integration. U is 2x, du is 1/2 dx. So that's where I get the 1/2 u. So at the very end, I have to plug back in my u. All right, so what would you do here?
I would break it apart.
Yeah, you're going to break it apart. So we're going to say 1 over cosine of x plus sine of x over cosine of x dx. Quotient identity. What is 1 over cosine?
Sine.
Secant. And what is sine over cosine? Which both have derivatives, by the way. They're not pretty derivatives, but this is a natural log, right? Natural log of what?
Cosine. Wait. Secant plus tan. Oh.
And this is a negative, right? Negative natural log of cosine. Right, so if you have like a numerator like this, expand it because you may be able to split it up at that point and then start doing something. Separate your numerator, just like we did on this last one here. If you have this guy, 1 over and x over is going to be easier to do because here now we have a natural log. Well, not necessarily. Actually, you have to do something else here. But here you have just a u substitution. Okay, so makes life a little bit easier. Complete the square. This is something that people don't always think about. But when you have a square root and you think, oh, this could be an arcsine or arctangent or something like that, or you have almost a perfect square, you can use completing the square, the wonderful method that we use to solve quadratics to make it a perfect square. You can actually do as well. And so completing the square is one method. Dividing is obviously one that you see a lot. Adding and subtracting terms in the numerator. Again, this has a problem because I have the 2x, and if I take the antiderivative of the bottom, the derivative of the bottom, I'm going to have a plus 2. Well, put the plus 2 in there, just subtract it back out. And then you're going to have a perfect u substitution and a natural log, or either this is to the second power, so you don't even have a natural log for that one. That's just to the negative 2, right? And so you can just take a regular derivative there. Trigonometric identities. When you have something that you don't have an antiderivative for, but its identity would rewrite it, and you do have a derivative for, an antiderivative for, you want to rewrite it. And then multiply and divide by the conjugate. This is a method that we use when we're proving identities as well, is using your conjugate to get it to 1 that then you can rewrite potentially. 1 minus sine squared is cosine squared. Well, we don't have 1 minus sine squared. We have 1 plus sine x, but we could get it to 1 minus sine squared using a conjugate. And then we could potentially rewrite it and solve for it. That method. So just like on the one where we added and subtracted, you actually multiply the top and bottom here. They actually multiplied by e to the negative x. Basically, if they had multiplied by e to the x, you would have gotten e to the 2x, and that doesn't help either. But if you multiply by e to the negative x, then it's going to cancel out of one of those and put it in the other, and it will also put it on top. So that's why they did negative x here. All right? So if I had just said multiply top and bottom by e to the x, I still would have had a problem, because this on the bottom would have been times e to the x. Well, e to the x times e to the x is e to the 2x, right? And I still have a problem, because then I have e to the x on top and e to the 2x on bottom, okay? And so I still have an issue. And so instead of doing that, they actually multiplied top and bottom by e to the negative x. And what that does is I still have an e to the negative x on bottom, but I also have an e to the negative x on top. So multiply top and bottom by e to the negative x. And on the top, you can actually pull that 5 out, because he's just a constant, so you can just put him here. And you have e to the negative x on top. On the bottom, when I multiply e to the negative x, 3e to the x times e to the negative x. Remember, you add your exponents. It's x plus negative x, which is 0. So you just have 3 minus, and then you multiply that 2 by e to the negative x. And so now you have actually a pretty easy u substitution. If my u is that denominator, 3 minus 2e to the negative x, then my du, this is going to 0 out, and it's just going to be 2e to the negative x times that negative 1 dx. And I don't want the 2 in front of it, so I have to multiply both sides by that negative 1/2. So negative 1/2 du is going to equal e to the negative x dx, which is my numerator here, e to the negative x dx. I can substitute with this, the negative 1/2. All right. And so I can pull the negative 1/2 out. So we have our negative 5/2 here. And then I have just 1 over u du. That's an easy antiderivative, right? That's just natural log. So I end up with negative 5/2 natural log of my u, and we can just replace that u. And then plus c. All right, so I would split this one up to 1 over sine of alpha plus cosine of alpha over sine of alpha. Because, you know, alpha's fun to write over and over.
Is it fine if we change the
To x, yes. 1 over sine is which one?
That's cosine.
Yep. And then cosine over sine is cotangent. And these both have antiderivatives. Cosecant is going to be the negative natural log of cosecant plus cotangent. And the antiderivative cotangent is natural log of sine.